Okay, so we're going to go over this idea of continuity. Now, I'm sure in algebra we've defined continuity as a graph you can draw, without any lifting of your pen or pencil. Right? And if you did have to do that, we said it was discontinuous. Now that can occur in different ways, right? Maybe there is a hole in the graph, right? And this is what's called a removable discontinuity. Right? Or maybe it had an asymptote where the graph looked something like this. Okay, and in both of these cases, we said that it was discontinuous at that point. Okay, so what we're going to do now is we're going to kind of reframe that in terms of our limit, more of a calculus view. All right, so we're going to define continuity at a point. And that's going to be the limit as x approaches a of f of x is equal to f of a. All right. Okay, so the continuity of point would be if this holds. All right, so if we're asked to determine whether a function is continuous at a point, then we're going to there's going to be a three-step process. Right, so we're going to define that as the continuity checklist. Okay, and then we're going to say that in order for f to be continuous at a, right, where a is again some arbitrary value, the following three conditions must hold. The first one, here, let me do a little bit of contrast here. Let's use a different color. The first condition is f of a is defined. Right? In other words, I can evaluate at a and I don't get something that is that is undefined. Right? I get a real value as an output for the function. The second thing is that the limit as x approaches a of f of x exists. Right? And the third thing is putting 1 and 2 together. The limit as x approaches a of f of x is equal to f of a. All right. Okay. Now we need all of these three in order to have continuity. All right. So all of the three must be satisfied. Okay. And as we can see why that must be the case, we can here just some examples of some graphs that have maybe one out of the two. So let's say here, you have a graph, the case where we have a hole in the graph. Let's say this is a. Now in this case, f of a, if this is our function f of x, is undefined. So it fails our first list in the continuity checklist. So it is discontinuous there, right? Although we could see it does satisfy the second condition. This does exist, right? Because as we could see, values that are near A are approaching whatever this value happens to be, right? Right, we'll call it L. It does exist, and the limit, in fact, for that is equal to L. So the limit does exist, but f of A is undefined. So it fails one of those in the continuity checklist. Right? So another way it could fail is if we have here, let's say this is our f of x. All right, and in this case, we could see f of A is defined. Right, it takes on that value there. All right, but what it does not have is that the limit as x approaches A of f of x, this one is undefined. All right, and as we can see, why is because the limit as x approaches A from the right side of f of x does not equal to the limit as x approaches A from the left side of f of x. Right, both of these are approaching a different value. Right, so again, the only way that the limit exists is if the one-sided limits are equal to each other. All right, so in this case, it is undefined. So it fails the the second of our continuity checklist. All right. Now, in some cases, we might have the first two. Say we have something like this, where this is f of x. All right. At A. Now, in this case, we have f of A is defined. Right, that's this value here. All right, and we also have the limit as x approaches A of f of x. That is also defined, right? That is equal to L here. Right, some constant, right? But it is defined, so we have 1 and 2. All right, so we say, all right, that's good, but that's still not enough, right? What we do have here is that the limit as x approaches A of f of x does not equal to f of A, right? As we can see, those are two separate values. Okay, so we do need all three of those to be satisfied, right? In order to say that a function is continuous at a point. Okay, so that's the definition of continuity. Now let's go over some of the rules of continuity, right? So luckily, if we have some continuity rules, it's a different color here. Continuity rules. Okay, so if f and g, now this will allow us to kind of classify a whole family of functions moving forward here. If f and g are continuous, at A, then the following functions are also continuous. At A. Okay, so if we have two separate functions, we can actually perform our basic arithmetic operations with functions. So the sum of two functions would also be continuous. The difference of two functions would also be continuous. A constant multiple of functions, c times f, right, where c is just any real number. All right, and that's what that notation means, right? C is an element of the real numbers. All right, and a multiple of functions f times g would also be continuous, and so would a quotient of f and g. And again, whenever we divide, we also just make sure that as long as g of a is not 0 to avoid division by 0. And also any power of the functions, that would also be continuous. All right. Okay. All right. So knowing that, that means that we can use these continuity rules to have this whole family of functions that we are just going to assume are continuous. Right? So the first family here is polynomial and rational functions. Okay, and again, a polynomial function is anything that has a positive integer power, right? So something like x, right? This would be a polynomial, right? X squared minus 3, that would be a polynomial. X to the 8th minus x to the 7th, and let's give it some coefficients. Right, these will all be examples of polynomials. Okay, usually, so what we can say is that all polynomials, a polynomial function is continuous for all x. All right. Okay, so that's why we like polynomials, right? It's continuous for x and it for all x, and as we'll see in later chapters, the next chapter is when we talk about differentiability. They're also differentiable everywhere. So those are nice functions that are easy to work with. All right, and also rational functions. And a rational function is just a polynomial divided by another polynomial, right? Where p of x, both of these are polynomials. Okay, so a rational function is also continuous as long as, again, always at division we have to be careful, is continuous for all x where the denominator, we'll call it q of x, is non-zero. Okay, when it is 0, that'll come up in the form of either a hole in the graph or some kind of, or a vertical asymptote. Okay, so we just have to be careful with that. But if its denominator is not 0, then it doesn't matter what the other values are, it will be continuous, as long, again, as the denominator is not 0. Okay, the numerator can be 0, that's fine. That'll just give us a function value of 0. We just cannot have 0 in the denominator. Okay, all right. Okay, and other types of functions that we can assume continuity here. All right, so we looked at some of our basic ones. Now let's look at our composite. So continuity of composite functions. At a point. Okay, so if g is continuous at A. And F is continuous. Now this one is a little bit tricky. If I can remember how to spell continuous at G of A, then F of G of A is continuous at A. Okay, now remember these are different kind of operations of functions, right? So if we have our function, let's say this is G of X, and if that is continuous at A, satisfies the three conditions here, then what we could say about this is we have to make sure that if we have F of X, that it is continuous not at A, but at G of A, right? Whatever this value happens to be. Okay, and if that's true, then the composite F of G of A is continuous at that point. Okay, all right. So now the next thing we want to talk about is this idea of continuity on an interval besides a point, right? So continuity on an interval okay, so say we have a function like this, where if we choose any point here in the interval A, we know that right, any point on some interval satisfies the continuity checklist. All right, like if we recall, we said the polynomial functions were continuous everywhere. So the interval for that would be -infinity to infinity, but we can also choose a finite interval, and any subinterval would also be continuous. All right, now in this case, we do notice that if the interval is from here to here, that the endpoints, right, will not satisfy the continuity checklist, right? Mainly the limit part of it, right? As we don't have a two-sided limit, we only have a one-sided limit at the endpoint. So there we define continuity at endpoints. Right, and for that we'll say that a function f is continuous from the left if the limit as x approaches a from the left side of f of x is equal to f of a. All right, and we could see that happens here. All right, if a is our endpoint, right, while the limit doesn't exist, the left-sided limit is, and the function is not defined on the right side. All right, it's simply in that interval. All right, and then we could say f is continuous from the right. From the right at a if the limit as x approaches a from the right side of f of x is equal to f of a. Okay, and that we can see happens here, right? Where it is continuous from the right side, right? And the left side, the function is just not defined at all, right? For any points. Okay, so when we want to say that a function is continuous on an interval, right? We'll say that a function f is continuous on an interval interval I if it is continuous at all points of I. Right, and I is just some interval, right? So in this case, we could say this from here to here, that is what I'm calling I, right? Whatever those values of the endpoints happen to be. Now the interval could be open or closed, right? And if it happens to be a closed interval, in other words, if it contains its endpoints, so we're saying that the interval is closed, continuity on I means continuous from the right or left at the endpoints. Left at the endpoints. Running out of space here at the endpoints. Okay. All right. Okay, so that's what we mean when we're talking about continuity. Again, remember, right, this idea of continuity is similar to what we've been taught in algebra. We're just reframing with the vocab that we've learned in previous sections of limits. And so when we're asked in this course about continuity, right, I want you to start thinking about it in terms of limits, right? Does it satisfy those 3 points on the continuity checklist? All right. Okay, so the last kind of types of functions that we're going to talk about here are root functions. All right, and just kind of define where we can assume that these are continuous. All right, root functions, so something like this, or cube root, or even something like this, where we have a rational exponent that's in lowest terms. All right, so whenever in the next whenever I'm referring to rational functions or rational integers, I'm always going to assume that it's in lowest terms. If it isn't, then you can always reduce it to lowest terms to make sure that we have something that's in lowest terms. And again, something like this means or. Okay, so that's what it means when we have a rational exponent. Okay, so if we have a root function, right, some function f of x, and it's raised to some rational exponent n over m, all right, and again here we're going to assume in lowest terms. Okay. So here we can assume here if m is an odd integer, so we do have to be careful here when we do have odd integer as opposed to even, again, this is 2. That when it's an even integer, this does need to be positive. But when this is odd, there's no restrictions here. Right? So if m is odd, and again, the power that it's raised to does not affect the continuity. It'll be continuous on any powers of n, regardless of whether it's positive, even or odd. So, but if m is odd, then this composite function, where we raise it to n over m, right, is continuous at all points at which f is continuous. Okay, since I'm okay having a negative value when I have an odd root. The only thing we do have to be careful of is when if m is even, then this composite function is continuous for values at which f of a is positive. Or, yeah, positive. And actually, here I believe we can actually say we can take the root of 0, positive or equal to 0. Okay, so for example, let's say that we have 4 minus x squared. Right, that's a polynomial, so I know that's continuous everywhere. And if, let's say, I take the cube root of this, that does not change the continuity. It'll still be the same as whatever the continuity of 4 minus x squared is. Right, so this will still be continuous everywhere. On interval I, in this case, the interval I is all real numbers. Right, but if that were, let's say, a positive root here, even root, then this is not continuous everywhere. Right, if we recall 4 minus x squared, that looks parabola here, where this is negative 2 and 2. All right, now in this case, this is the continuity is affected of only where f of a is bigger than or equal to 0, and that would be for graphically values above the x-axis. So this continuity changes. This is continuous on the interval I. In this case, the interval I is from negative 2 to 2. Okay. Any values up, let's say at 3, we get 4 minus 9, we get negative root 5, which is not a real number. Okay. All right, so that concludes here the topic of continuity and limits.